All right, friends, now comes kind of the crux of the whole matter, okay? There's a lot of parts to this. I know it takes a little while to build up, but we're getting now to the big cymbal crash, to the point. What we really want to know is under what conditions do you get a bright fringe, and under what conditions do you get a dark fringe? Perhaps I could have said that earlier. That's what I want to know. That's what I want you to understand. Under what conditions do you get a bright fringe, a bright spot on the back of the refrigerator box, and in what conditions do you get one of the spots between where there is no light, a dark fringe? Here's what you need to know to start off this little piece. A bright fringe is where there is constructive interference. Can you hear that crow out there? I bet you can't. I can. There's a crow right out there making some racket. Bright fringes, like point P, like the central max, are constructive interference. The dark fringes are where peaks and troughs meet up with each other and cancel each other out. Like in video 1, talking about the water waves, when the peak and the trough met up, they canceled out. So there was no wave. In this case, because these are light waves, that means no light. Dark fringes, destructive interference. That's what's going on. There are alternating points as we move up and down the screen, alternating points of constructive, destructive, constructive, destructive, constructive, destructive, constructive, and so forth. So at point P, we have a situation of constructive interference. I put point P beside a bright fringe. So there's constructive interference going on there. Okay. What we have to keep in mind, sorry, I started walking off to the side. What we have to keep in mind here is that these are not just rays, they are waves. So let's draw some little waves, and I'm going to draw them kind of small. Okay, I'm going to count them as I go, see how well this works. Okay. We're going to start with slit number 2 and draw a wave all the way up to point P. All right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I put 14 wavelengths between. So R2, let me erase this. R2 is 14 wavelength, whatever the wavelength is. It could be 500 nanometers, it could be a picometer, we don't know what it is, doesn't matter. I've drawn in that distance there, 14 wavelengths. Now I want to do the same thing between the first slit and P. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So R1 is 11 wavelengths. They are different lengths. Okay? But notice that the path length difference here is 3 wavelengths. I squeezed in 3 wavelengths in the path length difference there. Okay. Now, here's the condition for constructive interference, for a bright fringe. Path length difference, which is R2 minus R1, has to equal M times lambda, where M is an index. This is the first time we've seen an index, and it's a little bit of a confusing idea. M equals 0, plus or minus 1, plus or minus 2, dot, dot, dot. It's an integer. If the two path lengths are different by an integer number of wavelengths, as they are here, right? That's the path length difference. It's 3 lambda. 14 minus 11. It's 3. If that path length difference is equal to an integer number of wavelengths, then when they arrive at the screen, they arrive in step with each other. And when they arrive in step with each other, peaks meet peaks, and you get constructive interference. Troughs meet troughs, and you get constructive interference. If that path length difference is equal to an integer number of wavelengths. In this case, m equals 3. Right? In this case. This is just going to be, let me see, this point here is the m, oops, I think I've got room to do this. Point P is the m equals 3 maximum. M equals 3 constructive interference. This is m equals 2. This is m equals 1. The central max is m equals 0 because the path length difference was 0 lambda, which equals 0. 0 times anything is 0. So the path length difference for the central max is 0. Down here, this is our m is minus 1, m equals minus 2, m equals minus 3. M is not a variable. It is an index. All values of m are occurring all the time. All m does is tells you which maximum we're talking about. Which bright fringe we're talking about. Put it that way. All m tells us is which bright fringe we're talking about. It's a label. It's like me coming into class and giving each one of you a number. Number 1, number 2, number 3. Keep those numbers the rest of the semester. That's your index. That just is a way of me figuring out which one of you is which. Okay? It's a way of labeling you. All these values of m are happening all the time. There's an m equals 7 bright fringe up there. There's an m equals negative 12 bright fringe down there. I didn't draw it, but it's there. Okay? This is the condition for constructive interference. We also know that delta is d sine theta from the previous video. So we can set these two equal. D sine theta is m lambda. That is the condition for constructive interference, where m 0 plus or minus 1 plus or minus 2 dot dot dot. That is the condition for constructive interference. Any point on the screen for which this holds, for which this is true, remember, theta indicates the position on the screen. The original theta right here, the yellow one, it's a way of indicating where you are on the screen. So every point on the screen has a unique value of theta. If this is true for any point on the screen, you have constructive interference. I'm not going to derive the condition for destructive interference, only to say that in a case of destructive interference, you have to have a half number of integer wavelengths in this distance here. Okay? So that when they meet at point P, one is peaking while the other one's bottoming out, and you get peaks with troughs like this, and they meet at some point where they constantly are destructively interfering. Okay? In that case, let me see if I can do this here. I think I can do this. I know I'm going a little bit over on this video, but not too bad. So that's destructive. I mean, that's constructive on this side. For destructive, delta R2 minus R1 equals M. Not going to have room. I'm going to take that R2 minus R1 out. That's not important. Delta is M plus 1/2 lambda. So that's 1/2 lambda, 3/2 lambda. If that path length difference is a half number of integer wavelengths, 1/2, 3/2, 5/2, 7/2, etc., then you get destructive interference. And M has the same set of values. Okay, so in that case, d sine of theta is M plus 1/2 lambda. So how's that showing up? Yeah, that's okay. This, ooh, that was a nice sound. Destructive interference. If this condition is true for any point, hi there, if this condition here is true for any point on the screen, you get a dark fringe. Okay. So these are bright fringes. And these are dark fringes. Okay. All right. I'll say one more word next lecture, next video, and then we're going to do a example.